Okay, so let's get started. So welcome to this last day of our workshop. And as Massimo explained yesterday, Dario will not give a talk. So we have shifted the schedule a little. So we will end earlier at 3. And in the morning we will have 2 presentations and then the roundtable discussion. And we start with Ramin Golestanian, who will talk about optimal navigation strategies for microswimmers on curved surfaces. So please go ahead.
Okay, thank you, Kristian. So I'll talk about optimal navigation strategies for microswimmers, and the emphasis mostly will be on the geometry of the landscape for the microswimmer, but then I'll talk about some other aspects as well. And this is mostly work done by a PhD student in the group, Lorenzo Piro, and 2 group leaders, Evelyn Tang, who left us, and Benoit Mao. Okay, so to motivate the problem, navigation is a very interesting and important problem. In fact, in different communities, people look at navigation problems and optimal navigation. You can imagine that living systems rely on good strategies to find a source of energy, food, light, and so on. And of course, if they are developed and they have information processing capability, they will be better off doing that. But already down to the level of bacteria and tiny microorganisms, they have to do this, and they have evolved to have basically feedback mechanisms, nonlinear feedback mechanisms, coupling some kind of information, local information source to their motility mechanism, and essentially use this to navigate efficiently. There are, of course, nowadays also applications of these ideas, because people are making microswimmers for targeted delivery of drugs and genes and cargo, or environmental monitoring or cleaning, and so on, sensing of dangerous molecules, things like that. And essentially, the focus so far mostly has been to develop motility strategies or motility mechanisms that work, and essentially powering these. But ultimately, you want to also make sure that you don't have to take them by hand from A to B. You can enable them to have a mechanism to basically navigate themselves. So that's an interesting problem from the application point of view as well. And there are several directions that people have taken. For example, recently there were a couple of works using reinforcement learning algorithms to basically design microswimmer strategies. A good example of this kind of navigation strategy and adaptation, in fact, is phototaxis of algae. For example, so algae are essentially light-seeking. You can see here the photograph, the algal bloom in the southern coast of England. Essentially, they can form very large-scale structures, but ultimately, individually, they basically seek light for their source of energy and metabolism. And for this particular one, Chlamydomonas, it is known that the algae has one so-called eye spot on the side, in fact, not at the front. So it's not like the eye, which is on your forehead or your face. And somehow it can use the intensity of light as measured by this eye spot to navigate its strategy when it is going through the so almost strokes breaststroke-like cycle of swimming, and the way it does it is by essentially spinning around itself, and that creates an oscillatory pattern for the intensity which is measured, like a radar, for example, in an airport, and then essentially tilting at an angle and making sure that the oscillatory signal basically remains at a constant intensity. And it's possible to develop a model. So here we looked at, with my former student, Rachel Bennett, we looked at a 3-sphere model in which basically the stroke of these cilia, which were modeled as beads, essentially were coupled. The harmonic that is driving, the first harmonic that is driving the motion was coupled to the light intensity in a very minimal way, and we could show that this was already enough to essentially lead to an adaptation and orientation dynamics which will go towards the light even if you basically take it away or throw it away and switch on and off the light and so on. So it's possible to in fact study and propose mechanistic strategies that will do the measuring and couple this information to the motility and in fact create a robust navigation strategy. In addition to reproducing other features for the chlamydomonas dynamics. So this was the observation of run and tumble and basically stable swimming and synchronization of the two cilia and so on. Okay, now navigation is an old problem. You probably know about the so-called Zermelo's navigation problem. This is essentially formulated here. So imagine you're steering a ship and you want to go from A to B. How do you do that? So that you basically minimize the time given a velocity for the propulsion or the speed of the propulsion, and essentially some kind of landscape. So U and V are here components of the flow field in 2D. And Zermelo showed in this paper already in 1931 that you can use this equation to steer essentially the orientation of the ship through this landscape, and essentially the coupling is coming from the derivatives of the velocity field to the orientation. So what we did recently was to look at this problem on a curved surface. Here you essentially start having interesting possibilities because this optimization is all about distances, and distances basically on curved manifolds will start to become basically non-trivial in the sense that, for example, it could be that going from A to B can have more than one possibility. So you can have alternatives and things like that. So here is the setup of the problem. Imagine you have a manifold M, and basically you're looking at the trajectory R of t, or tau, along this, and then at every point you have a self-propulsion V naught, and the magnitude of that is fixed, but you can choose the orientation. And then you have a force field, which is stationary at every point of the manifold. And basically, you can write down a sort of first order kinematic equation, let's say, for the overdamped motion of this self-propelled swimmer or microswimmer in this environment. So let's say the manifold has this intrinsic metric Hij, and that means you measure the scalar product of any two vector belonging to the tangent space with this expression. And you can also define the line elements, which will measure the length and will have information about the geometry, which you can take from one point to another. So assume that we can have full control over the orientation, and the question is, what is the optimal path that takes us from basically A to B on this space? So we can formulate this using the travel time, which we can construct basically as this integral of the line element divided by the local speed. And then basically treat that as a Lagrangian and try to optimize this action, which is time basically. So here we are using a notation where dot shows basically dr by ds, and the speed is essentially ds by d tau, which is variable. So this is not always the same as v naught, which is the fixed propulsion speed. So you can rewrite this Lagrangian, which is essentially the inverse of speed, in this form. Basically, this is a simple manipulation of the equation of motion, which we had here. So essentially, we know that this velocity has a constant norm and things like that. So we can manipulate the equation and extract this effective speed, which will have this form. These coefficients, so Aij and Bi, are essentially functions of the metric of the self-propulsion velocity and of the force field that we have in the system. And you can see that essentially this Bi term is controlled by the force field, and Aij is essentially something like the metric of the background manifold, but it also has information about the force field. We basically can make the observation that this Lagrangian is uniform with respect to r dot of the first degree. So that means, you know, if we scale r dot with something, we essentially scale both terms the same way. And this is a property that you can use to construct a specific type of differential geometry called Finsler geometry, which doesn't have the standard Riemannian structure for the metric, in the sense that the line element is not a quadratic form of, you know, is not proportional to r dot I, r dot j with the metric tensor G, but it is a function which has essentially homogeneity property, a scalar function. And then from that scalar function, it's possible to extract geometric properties, which I will show later. So this basically is observation number one. Observation number two is that this is a specific class of Finsler metrics. It's not basically one that essentially respects the, let's say, time reversal, or in this case, the line element reversal property. It's called the Randers metric. And in fact, this has been studied by Randers in 1941 in the context of possible generalizations of general relativity and unification between electrodynamics and GR. You can clearly see from this expression for lambda that basically if the strength of the external force field competes with the self-propulsion, we are going to have a problem with this definition. Essentially, we need to decide whether self-propulsion is always able to overpower the external force or not. There might be possibilities where the external force will be stronger. And in this particular class, in this particular work, we basically restrict ourselves to the class where the self-propulsion is always stronger than the external force field. And that is essentially very convenient because it means that the swimmer can go anywhere it wants. If this condition is not satisfied, then the swimmer can get trapped into basins of attraction where basically the external flow field is stronger than the propulsion. And in this deterministic condition, that means, you know, that part of the space will not be essentially, yeah, it will be like a black hole. If the particle goes in there, it will never come out. For simplicity, we essentially made this assumption, but there's nothing fundamentally sort of wrong about that other possibility. And in fact, we are looking at it in further work. So if we make this assumption, then this metric is convex and positive definite, and we can essentially define a fundamental tensor from this second derivative. And then basically, for all intents and purposes, this fundamental tensor will behave like a normal Riemannian metric tensor. In particular, as we will see, we can basically minimize this action. In fact, it's more convenient to minimize L squared instead of L. But the Euler-Lagrange equation that you will obtain for L squared is the same as what you will obtain from L for L. And then when you write this equation for something you can call energy functional, you basically obtain a geodesic equation for the Randers metric. And the definition of these Christoffel symbols essentially is the standard definition that you have in Riemannian geometry, except that this G IM now is the one that you obtain by taking the second derivative of this L squared with respect to our dot. And you know, if you remember what L is, this is square root of R dot squared plus a linear term. If you square that, you get a quadratic term, but you also get R dot times the square root of R dot and this R dot squared again. So that product between the R dot and the square root will give you a term which will never go away, essentially, and it will always give you velocity dependent metric tensor, and all the higher derivatives, Christoffel symbols and so on, they will continue to be velocity dependent. And this is the specific feature of Finstler geometry. Okay, so, but you know, it's quite nice that we have a geodesic equation which we can use. You know, now you can essentially go back and specify any geometry that you want, and immediately you will have the optimal geodesic that will take you from point A to point B. And now we will look at this in basically for a few examples. So just to summarize what we will do, we will choose a space. That means defining a metric tensor. We will choose a force field and then make sure that the speed is always stronger than the magnitude or the strength of the force. Then build the Lagrangian, the Randers metric, and then from that we calculate geodesic equation for the Randers metric, and then identify points A and B, the initial and the final points, and then basically solve the differential equation, the ODEs, in order to find the best trajectories. So we'll do that for a few examples just to see what kind of interesting information we can obtain from this formalism. So let's look at a sphere. For a sphere parameterized by theta and phi, you can basically calculate the metric tensor like that. And let's take this force field, which is basically in the azimuthal direction. So it's essentially always spinning around and changes with theta, and the strength of A is less than V naught. Then we need to solve this, and we will do that using the shooting method instead of essentially fixing it at 2 points. We will start from 1 point with different velocities and then categorize the trajectories based on where they land. Now, a good first observation that comes out of this calculation is essentially this notion that Randers metric here is non-reversible in time. And you can see that, so this is essentially a consequence of the, or it's a reflection of the out of equilibrium character of the problem. You can see it in this problem when you solve the geodesic between 2 points on a sphere. So here, look, if you look at the sphere and you want to go from basically the green point to the magenta point, the geodesic will be this dashed line with blue arrows. And then when you go from the magenta point to the green point, the geodesic is different. Essentially, that is simply a consequence of this term, which doesn't have the symmetry of r dot 2 minus r dot. And a nice second observation that comes out of this is the fact that the travel time could have sort of discontinuities if the system starts to use or take advantage of singularities in the flow field. So here, for example, you can see that the irreversibility, if you want, or the measure of non-reversible character of this metric can be measured in terms of the enclosed area between the forward and the backward trajectories. You can see that it increases linearly almost with the amplitude, and then at some point there is a discontinuity. And this discontinuity corresponds to an amplitude at which basically going between these 2 points is advantageous, essentially if it happens around the vortex. So let's say one of the paths takes one trajectory and the other one does it so that essentially the full cycle encloses now this vortex at the pole. And then it turns out that exploiting the flow structure by, let's say, encapsulating the vortex or something like that could have consequences for the travel time or the optimization problem. For example, here you can see essentially going from the green point, starting point, to the target magenta point. There are 2 different policies.
Sorry, Ramin.
Yes.
So there is a question in the chat.
Yes. Okay. Let me look at it. Okay. So Klaus is asking, is this any worse than a Coriolis force? So what do you mean, Klaus, in terms of worse?
Well, if you are on a rotating globe and you go back and forth, you have the Coriolis force, of course, and that also distracts your optimal path. So my question was basically whether there is a similarity between the 2 things, or how far.
So the Coriolis force is indeed velocity dependent, but you know, we tend to think about it in terms of inertial navigation. Basically because the origin becomes relevant. This is essentially all in the dissipative regime, and the flow is just randomly chosen. Yeah. So I think, I mean, when you have a flow and you're essentially and the force is velocity dependent, and you write down an equation of motion for the inertial dynamics, then of course the velocity dependent term will also break the time reversal symmetry.
Mm.
Yeah. Okay, so if you look at this, so thanks for pointing out the question. I mean, I have an eye on the chat, but I think it's better if someone or even the person who has the question, maybe you can just unmute yourself. It's not such a big audience. So if you look at this case on the top left, essentially the two different policies are being compared. So you have this Randers policy, which is the solution to the geodesic equation, and or so-called Randers policy, and you can also have this direct policy in which basically the swimmer is looking at the target at every point and going straight to this point, to this direction, or to the direction of the destination. You can see that basically at small flow amplitudes, actually that is not such a bad policy. The comparison between the blue crosses that correspond to the Randers policy and the red dots that correspond to the direct policy. Up to this point, and by the way, this TR is the time it takes to go from A to B, essentially without any flow. So following the normal geodesic of the manifold. At this point, something happens, and basically you can see that the Randers policy starts to enclose the vortex and take advantage of it. And essentially, when it goes around, it can start using the flow field, and you can see that there is now a significant gain in terms of the overall travel time. And then essentially in this green region at much higher amplitudes, even the direct policy now has to enclose the vortex because the flow is simply too strong. Okay, now let's look at another example. So here you want to go to diametrically opposite points on the sphere, and you're seeing the front of the sphere on the left and then the back of the sphere on the right. And as you can see, there's a similarity here to the previous example, but in this case, actually the flow is always helping. And even the direct policy, when it's doing worse than the Randers policy, it's still essentially less than 1. But still, you can see that the Randers policy is very efficient, essentially by taking advantage of the flow. Right. Then, because the flow structure could be complicated, one way to start thinking about the range of possibilities is to look at isochrones, so the curves of equal travel time. You can imagine you start at a given point, and then you basically look at the collection of lines that can be the endpoint of the trajectory at a given time. So here 0.2 is this green circle, and then at later times you start to see that the flow is going to essentially deform this trajectory. And then at some point, the trajectory starts to self-intersect because there are basically many opportunities to essentially follow at the same time different trajectories depending on the initial orientation. And one of the features that will come out in this case is the appearance of these cusps, and essentially you can see that these cusps will have interesting features. Another feature which we can see, for example, in this case, let's look at this panel on the right. If you start from the green dot and change the initial condition just a little bit, but for trajectories that can go through this vortex, then you will see that they all start essentially on the same path to come to the vortex, but then a slight initial change in the angle can create basically a lot of different trajectories. And this kind of sensitivity, again, could be something that can be exploited, let's say, by the strategy. So the vicinity of these cusps will have many geodesics, simply because by definition, these are the places where you would have multiple solutions. And you can see that in this animation. So here you can see that there are two trajectories that start with different angles and then end essentially at this point on the cusp, and that's how we constructed these isochrones. So it's quite natural to expect this. If we change the flow field, for example, with this one, we can see a situation where the isochrone is even discontinuous. You can see it here, for example, that it's not necessarily the case that the endpoints are connected. And the right panel, so you can see these complicated intersections. The right panel shows the issue of sensitivity to the initial condition again. So you start from here, you go through the vortex, and then depending on tiny changes, you can basically follow one of these two paths. Right, and then essentially, as you would have expected, it's also possible to take advantage of the geometry and have a situation in which basically going around it could be advantageous. So in this case, these 2 points are relatively close on the sphere, and at small amplitudes, basically the direct path is the best path, but then beyond a certain amplitude, it's actually beneficial to go around and take advantage of the flow field, and that will give you a smaller travel time, as you can imagine. You can also do this on other manifolds, so I'll just go very quickly through some examples for a torus. So basically the same things can be seen. The notion of essentially enclosing the vortex and taking advantage of that, first for the Randers policy and then for both the Randers and the direct policy, and the notion of essentially going around, you can see it here in the case of the donuts case. So to summarize this part, basically we have this geometric formalism to describe optimal paths between different points on any manifold with any flow, and essentially control over the self-repulsion trajectory. And it's a nice connection between microswimmer physics and things that have been looked at in general relativity. And of course, it will be important to include additional features and basically make more use of this, especially, for example, to look at space-like paths where the signature of the metric changes and so on. Now I want to use the rest of the time to talk about the role of noise, and this is more recent work. Essentially, you can imagine that fluctuations are going to change the picture, because basically as soon as you have noise in the system, then arriving at a given point will also mean that you have to have the right magnitude or amplitude for the noise strength, and also maybe, if the situation is very specific, a very specific realization of the noise. And the right formalism to look at this when we are thinking about the time as being the quantity we want to optimize is, for example, to look at mean first passage time calculation. So from a Langevin equation, you can write down essentially an equation for the mean first passage time for an active particle, and optimize the policy such that essentially the time on average will be minimal or optimal. And then the equation you need to solve will be this one, which basically looks like the mean first passage time formulation in an external force field, with this additional term which comes from the self-repulsion, which includes the gradient of the mean first passage time as a function of the starting point. With the boundary condition that this function t at the target is basically 0, so when you arrive there. And the optimal policy essentially is given by the gradient of this function. So it's a formulation that you can use to solve numerically, basically, for the optimal policy. It would be good to look at a few examples, and also we wanted to see if it's possible to devise strategies that are local. So I will explain this a bit more. So imagine you have this Taylor green vortex flow at the background, and you want to go from the green point to the magenta point. Here you can see this green trajectory essentially is the optimal path. This blue trajectory is essentially a direct policy, and these are realizations of stochastic trajectories that essentially follow those policies, sort of more or less, let's say. There are two parameters in this case. So one is this flow velocity strength, Vf, and one is V naught, the self-repulsion velocity. And because as before we talked about this condition for V naught, this gamma parameter essentially will be always between 0 and 1. And then there is this Peclet number that we can define, which essentially brings in the a comparison between self-repulsion and the strength of noise D, which is the diffusion coefficient here. And this L, the length scale, is basically coming from the geometry of the flow. So first observation from this calculation is that for essentially a reasonable range of the noise strength, we obtain distributions from this calculation from the Fokker-Planck equation that stay very close to the Zermelo path. So this green line in this Taylor green vortex is the Zermelo path, which is deterministic. It doesn't have noise, and then basically you can see that it seems to be beneficial for the particle to follow that, but of course with fluctuations around it. And here you can see in blue the optimal orientation map. This basically tells you that at every point you should point in that direction to take advantage of the sort of optimal strategy for the navigation. However, in order to do that, we need to have basically feedback control. So at every point, we need to basically tune the orientation and know about the Zermelo path. We can try to think about, so instead of going for the full optimal policy, which is the solution to this mean first passage time problem, we can try to devise additional policies or different policies that are local, and they basically take advantage of the locally available information, and then see how well they are doing, essentially in comparison with this fully optimal solution with noise. And typically, this can be formulated using an alignment type strategy. So imagine the particle is sitting at a position R, and basically it knows about or it can identify the Zermelo path, which is the optimal path without noise, and then it can essentially point to the direction where it finds it first, or the shortest distance, and it can also measure its distance. If it uses a policy in which basically it only keeps an angle with this normal vector n, we call this an aligning policy, so one in which the distance doesn't enter, but it's just that the swimmer basically makes sure that it always has a fixed angle with this normal vector, and that angle can be non-zero, because otherwise if it's zero, it only goes towards that in a perpendicular way. So you want it to be somehow non-zero, so that there is also progress along the path. So we call it alpha. And then you can also imagine another policy in which there is adaptation depending on the distance, because if in fact the distance between the swimmer and the Zermelo path is very, very small, it's not really necessary to point in a very sort of a strong way towards the path. You can essentially align parallel to the path or to the tangent and just move along it. Whereas if you're very far from it, you have to go back to the path first and then take advantage of the parallel direction and swim. So you can imagine that an adaptive policy in which basically you measure the distance, and then using a threshold, you determine whether you are far from it or near to it. And then if you're far, you just move towards it. And if you're near it, then essentially you align with it. This would be essentially a more sophisticated policy. You can see here what happens when you change this threshold, epsilon. So on the left, you have a very small epsilon, and that means from most places, basically, the particle, the swimmer, will always try to go straight to the Zermelo path. When epsilon is relatively large, for most places, essentially, it will already start to move parallel to it without trying too hard to go towards it. And as you can imagine, there tends to be an optimal value where you can basically balance these two aspects. So, staying close to the Zermelo path and moving forward along it. And you can see this here in this calculation of the mean first passage time divided by the optimal time. So the optimal time is the optimal time in the absence of noise. And it's good that basically there is this optimal value, and then you can say for the flow field, you determine it and essentially use it for any swimmer that needs to do this navigation. Now we can compare the optimal policy with the straight policy, as we did in the previous part. Here you can see animations of stochastic trajectories. It turns out that straight policy in this case, where the straight path is actually going straight opposite against the flow field, is less optimal. And this can be systematically looked at. So as a function of this gamma, you can see here the comparison of the arrival time for 4 different cases. And the optimal policy, the triangles, of course, is the best. But you can see that this adaptive aligning policy is a very close second. And the information that you incorporate here is really very minimal. Just this notion that you need to stay in the vicinity of the Zermelo path, but a local adaptation of that. And then you can see that basically the aligning policy is a bit worse, and this straight policy in this case is quite far off. It's possible to look at the distribution of the arrival times, and it turns out that the distribution is basically very similar to a so-called inverse Gaussian distribution, which is the distribution for the first passage time of a 1D Brownian particle with a constant drift. And here you can see how well this distribution is doing as a comparison. And basically, so for different cases, and as a comparison, you can measure the distance, the Kolbe-Kleibler distance between the numerically obtained distribution, you can call it Pn, and this inverse Gaussian. And you can see that for most cases, essentially except for the aligning policy, it stays very, very close to this inverse Gaussian. So that essentially confirms that the idea of following more or less a one-dimensional geometry, almost like you know, these tube areas that are in the vicinity of the Zermelo path, will basically provide a very good policy in the presence of noise. The reason that the aligning policy is doing so badly turns out to be essentially, in terms of this comparison, connected to the fact that the distribution becomes strongly asymmetric around the Zermelo path. And then there's no, it's not surprising that it will not basically behave similarly to the optimal one. We can check the robustness of this. For example, here, the strength of noise is changed, and you can see that basically this picture, for example, the hierarchy between the different policies stays more or less the same. And essentially here you can see that depending on the gamma values and the Peclet number, which is the strength of the noise, the overall shape of the performance basically stays the same. But the optimal policy, of course, is doing better than the adaptive aligning one, for example, in this corner. Right, we can add noise to the sort of steering policy, and it essentially changes the picture to the orientation, changes the picture in a relatively simple way. Essentially, it just adjusts the projected velocity along this tube, and that seems to work well with the numerics also. And it's possible to change the task and make it more complicated and still basically have this kind of picture and generalize it to more complicated geometries by bringing in the background metric and essentially combining this idea with the previous part of my presentation, and that seems to work also with the same sort of structure. So essentially, the conclusion of the second part is that it's very interesting that you can devise local semi-autonomous strategies. So semi-autonomous because you need to know about the Zermelo path, which is the zero noise optimal path. But then once you know about that, you can implement a very good strategy just using local information without essentially having this external global control. And the performance seems to be almost as good as what you would get from the fully optimal mean first passage time calculation, and relatively robust also. So with that, I'd like to acknowledge the members of the group who did the work. So this was work done in the PhD thesis of Lorenzo Piro and Evelyn Tang, who was a group leader in the beginning and left, and then Benoit, who took over from Evelyn in the project. And thank you for your attention.
Okay, thank you very much for a very nice presentation. So we have time for questions. Do we have any questions?
Maybe I can
May I ask a question?
Sharing so that I can see you. Yes. Mm-hmm.
May I ask a question? I really enjoyed that talk, Ramin. Thank you very much. I had a question about the global versus local control. So if I'm correct in my understanding, in the first part of the talk, in order to determine the optimal routes on these curved surfaces, the microswimmer would need to have global knowledge of the flow field and the positions. And then in the second part of the talk, the microswimmer would need to have full knowledge of the Zermelo path, which would again require that global knowledge. And I guess I was interested on your comments on thoughts on how this would connect to applications of swimmers. I mean, I'm sort of thinking, you know, when the models of, say, run and tumble chemotaxis or bacteria is very much, these things are too small to know globally what's going on. But I'd be interested on your thoughts on that.
Yeah. So that's a very important point. And I mean, as you summarized, the main sort of advantage of the second part was to only require global information about the noiseless dynamics. So the essentially Zermelo path corresponds to zero fluctuations. It's the deterministic path, and then you know, you can have a very optimal, let's say, the maximally optimal solution by solving the corresponding Fokker-Planck equation, which requires the global knowledge and gives you a distribution. Still, it's a distribution, which means, you know, on the day there will be fluctuations when you make choices. Now, when it comes to organisms who don't know the global flow, essentially they will need to just do the best they can. So if you want to design, let's say, a microswimmer that carries a cargo, a gene, let's say, to a certain location in a patient, then of course that's a much more subtle task of a bacterium trying to find any food, let's say, anywhere. It's a different kind of problem, and for that you essentially don't need to know everything in the space. So I mean, another way to say this is the optimization problem depends on the level of accuracy that you require. And at the end of the day, there is no magic involved. You would obtain the best that you can under the circumstances, and you can just compare these the optimality of the different solutions in relative terms. So which one is more efficient and less efficient and so on. If you think about it, the same is true for global navigation. So as far as I know, airplanes at the moment do not really care about the sort of global sort of wind velocity when they want to find their navigation, or they don't optimize their fuels and things like that. Essentially, they have well-defined trajectories that they use, and they correct it on the day, basically.
Thank you.
Okay, are there more questions? So I have a question about the dynamics on the curved manifolds. I don't know if you mentioned it, but what is the main difference between optimal navigation on a flat manifold and the curved one? So you get new kinds of dynamics on the curved manifolds that you can't have on a flat manifold, or new kind of optimal trajectories?
Yes, well, I mean that's so the first thing that comes up on a compact manifold is that you start having many more solutions, so more possibilities, let's say. On a flat manifold, it's much less likely to create this situation where you will have degeneracy of, let's say, two possible solutions. And then yeah, I guess at some point you can also start thinking about well, taking advantage of geometric features. So the examples that I showed were essentially all constant curvature spaces, but you can imagine that you have a manifold which is not constant curvature. You have curvature structure, and then you can start thinking about devising strategies which somehow, as a rule of thumb, they know that using the curvature landscape could have also benefits and things like that. So it's simply, I mean, at this first, so these are the first two things that we did at this first step. Really the main progress is to have this framework which is geometric and it's general. You don't have to solve the problem every time from scratch by writing the Lagrangian and so on, and parameterizing it. You have a systematic way of doing it using the background Riemannian structure and standard tools of differential geometry, and then it depends on the specific problem that you want to solve.
Okay, thank you. So there's a question from Ganesh and one from Klaus. So let's start with Ganesh. So Ganesh, did you have a question? So you raised your hand, or is it?
Sorry, I had muted myself. Can you hear me now?
Yes.
Okay. So my question was, if one considers a fluctuating surface, for instance, the swimmer moves on a membrane, and so that the curvature is a function of time also, and stochastic. So I was wondering if the noise in the second part of your problem, would it in any way be a surrogate for the stochastic inputs that might arise from the fluctuating manifold?
Yeah, very good question. So yes and no. I mean, yes, in the sense that that will also correspond to a noisy situation, and no in the sense that if you start having time-dependent geometric features, then strictly speaking, you will have a multiplicative noise situation, because the metric essentially controls the strength of the noise as well. And in that case, you need to care a little bit more about the structure of the equations that you write, and there'll be spurious drift terms and things like that, which, you know, we haven't done at this point with these equations, but you can essentially do that. So you would be able to use or take advantage of these the machinery that exists for this kind of thing. Of course, I mean, this could have interesting consequences. We haven't done it, so I don't know what might come out, but you can imagine that you can, you know, you can speculate that there could be non-trivial things that you can obtain by sort of flickering or modulating or changing the geometry.
So there's also a question in the chat about can geometric topology affect the way a swimmer navigates? For instance, can the swimmer's navigation change from, say, a levy walk to Brownian motion when going from a plane to spherical geometry?
Yes, so certainly if it's time dependent, then it can go to a levy walk, or, you know, it can change the fractal dimension of the random walk, the exponent, make it anomalous and so on. By simply changing the geometry to a fixed geometry which is different, such as, you know, a compact sphere, I think the diffusive aspect will not change. You know, necessarily, but also it depends on the flow field that you have, because if you think about it, the problem of Brownian motion in a flow field in general, I mean, forget about optimality, forget about navigation, forget about geometry, is a complicated problem. You have to you can, if you have, let's say, a random landscape for the force field, you can have anomalous diffusion and various properties. And then if you add these things to it, of course, you can have additional features. But yeah, I mean, I guess all these questions relate to interesting things that can be done in the future. And yeah, I agree with all of them.
Okay, so thank you very much for presenting the very interesting work.